dear alumni, IDC alumni, and many of you, I may know some of you, but probably we'll get to know each other now. And I work for a company called Imaginarium, which is into enterprise 3D printing. And today I'll be talking about 3D printing, creating sensation. To make sense, it is a kind of a journey, when it started, it was creating a lot of sensation, but down the line, it is also becoming a technology to reckon with, and it can do a lot of wonders. So, in the beginning, we'll see some of the artifacts which are creating sensation, but down the line, we'll make sense of all this. That is the theme. And I have a disclaimer here. Uh, I'll be showing many companies, their products, and all that. Of course, I don't own any one of them. What we own is the narrative. That's all. And so here goes the sensational Black Lady. This we created very proudly for uh, worldwide media and the filmfare people. And the bird of the Black Lady was redesigned to be a blossoming, lotus. And you can see the lotus there. And this is a very unique piece because only the 59th Filmfare Trophy has this, and they're all very light. And it was the year was 2013, and the 59th Filmfare Trophy. Okay, and they were all made at Imaginarium by 3D printing. Okay, and so the whole Bollywood, Hollywood, and everywhere, people were trying to consider 3D printing as a great something fallen from the sky, that kind of feeling. So it had such a sensation creation quotient once upon a time. And of course, we went to various fashion show because fashion show also draws a lot of crowds. We went to the first Asian 3D printing fashion show. Can I request somebody to mute there? Okay, it was disturbing. The first Asian 3D print fashion show that happened in Kuala Lumpur also gave a ample window to the world as to what all one can do in the world of fashion. And I designed this peacock headgear, and it was one of the few designs selected all over the world, showcased at Kuala Lumpur. And likewise, there were many, So we have been trying to sponsor people who design things very intricate, trying to make it by 3D printing and all that, And in fact, a lot of new generation entrepreneurs have started making these artifacts without any inventory. They make it in CAD and then they host it, and they get order, and they order once they receive, it comes to us and we make it. Okay, we own the 3D printers, and we make all the material, the so-called investments and all. It goes finally, to the end user. And likewise, we have been empowering a lot of startups.
Paper pen.
You are seeing mostly jewelry here because I consider jewelry to be a sensational thing, a thing which doesn't function. Its function is to, is passion, love, and things like that. It's symbol of that. And so people do a lot of investment into all such things, and many of such things we have done. But that's not all. So this technology actually can do a lot of things. And these are combination of gold and nylon, for example. And see how primitives they have just taken, dropped down from the CAD software, and they're able to just have it as a piece of jewelry, where piece of jewelry is not even gold, it is nylon, polymers, it could be titanium. It is not bright, it is just silver gray color like that. And in fact, people have been wondering how we make this rapid manufacturing directly from 3D printing. Are we going to do it by directly metal printing? Things which are so intricate. And in fact, the kind of texturity you have with these material, they can be made as assembled, though you need to enamel them, you need to color them, you need to do certain for example, diamond setting is done later on. But as a bracelet, it is made as one. There is no assembly required. That means this technology is quite powerful. It can do a lot of things which were hitherto impossible to make. Well, I think at this point of time, I would like to jump. Whatever we saw so far, it is all it's all something making something, right? Products are made by someone, right? And so it is all about art of making things. So today's uh, whatever we are going to see, it is another art of making things. And humankind have been always looking at uh, you know um, from the primitive ages or whatever you have, prehistoric time, people have been trying to depict something. And so designing, record keeping and all started this way. And they started also making tools to protect themselves and to do killing on to so all these things are definitely, we all know. I don't have to dwell here. uh, we have a long way, and people have been keeping record keeping, counting and all started much before even they could speak, anything. And the journey of artifact, from a basic thing to the very fine vase, it's a long way, and so also these artifacts. And you can see many things, they retain the shape as it is, but they became much finer. The finish, what you have, it kept on increasing, and to a point, it became a state of art, you know. And in fact, the metal thing is also very interesting. Much before chemistry, alchemy, and all came, people were actually looking at metal, which were nodules occurring in the nature as it is. Just like stones, these have been, corroded, eroded, and rounded, tumbled in river beds, and people used to correct it. So copper or gold, for example, they were all found this way, and they also found their way to these artifacts. So these are some of the Bronze Age artifacts people have been using. And today, not much things have changed actually. Even today, people use wax, beeswax and all to make such artifacts. And we also use it today to do jewelry. A lot of jewelry is done by using wax. And so, in a way, it is technology, how to apply these material only are transformed, in a way. And with steel, iron and all, Iron Age, they were able to shape stones. And be it Mohenjo-daro, Harappa time, or very recently, about 300, 400 years back, people have carved these pillars, which are again very hard, but they were able to shape it because of the material property of iron, low carbon steel and all that. And so, if we rewind, we started with making pots of different kind, and even today we see this. And the handicraft, somewhere it is still there, but our hands are not capable of actually doing many things. Because of that, we required tools, in order to shape things. And whatever the environment around us, we started using them to our advantage. And this led to a cottage industry. Cottage industry needed more discipline. So this is a typical marketplace where you can even today find such artifacts, right? So they're all very born probably conceptualized long time ago. They are still living, you know. And the early factories were like this. Instead of sitting at home, the people used to come to a place called a factory, and they get this raw material, feedstock, and there are supervisors to take account of what they are doing, you know, or to help them if they want to. So that's how the factory used to look like without any machinery. But mechanization helped man to actually put in a lot of energy into whatever they are doing. So mechanical advantage was actually made use of, and soon it led to the steam power and all, and this we all know led to industrial revolution. This is typical industrial revolution picture. The Bombay city was also looking like this, with all the mills around, and this is Ford's assembly line. This looks like a tabela of a the um, what you call as cow shed. So one side the chassis used to enter, the other side it used to leave, with all the things put. Division of labor, line, production line, and all were born at that time. And but soon, with the advent of radio valves, miniaturization of electronics, the whole things changed. To have some kind of an automation. So what you're seeing is the electromechanical calculator, and but I think this is the last of its kind. Soon, transistors, miniaturization of electronics, all that started. Computing age started, and whatever we saw so far, we can call that as a production technology, art of making things. So, art of making things in modern terms, we call it as production technology. And when we call production technology, when we speak about it, there are only three ways anything can be made. You can make it or break it, and put it back. These are the, they say, you cut it, break it, or, glue it, or something like that. So, subtractive and joining is by gluing, or you can just transform or form it, bend it. So, formative. In fact, the today's topic, what we are discussing, 3D printing, is a subset of one particular pillar, that is additive processes. Many people also call 3D printing as additive manufacturing, though I'm not very happy with that, because manufacturing for me is a very loaded term. Manufacturing means making millions. We'll come back to that point. So if you take plus processes, casting, welding, cladding, painting, plating, gluing, lamination, coating, and 3D printing, these are all part of additive processes. What are zero processes? You neither add nor you subtract. Bending, extrusion, drawing, forming, forging, coining, rolling, knurling, embossing. They're all zero processes or forming processes. Then we have subtractive processes, like turning, shaping, milling, drilling, planing, broaching, trepanning, sawing, reaming, grinding, filing, chipping, and many more. They're all. So it is like, you have a stone, you're chipping out to uh, bring out a shape. That is all subtractive, but that is very wasteful. We'll see how. And in fact, people have been trying to, with all these processes, they're able to shape their ideas, shaping the ideas to make products, what we all use today. It has been happening. And we all know, I'll not go into the details of the design process and all, but just to say, world over, people have been going through a systematic innovation process beyond, recently we started calling it as design thinking also. But people have been doing this, And here, many times when you have an ideation and you go for a detailing nuts and bolts of design, you have to always test it. And many times we say, why a design has to be tested? You just do it. because there is a possibility design may fail, correct? No? And so that's where the prototyping becomes a very important aspect of production and design. And that's because there is a business case. What is the business case? The cost committed curve to cost incurred curve, or somewhat negative, right? Concept design, detailed design, you're not incurring so much of cost as much as you do when you make it or use and dispose. So there is a lot of cost is committed, cost incurred is less during concept and detailing stage. So people want to test here only when the cost is less, so that they can de-risk the whole process of product development. That forms the business case why people want to go. And in fact, if you look at these blocks, no, planning doesn't require any prototype, but in concept development, system level design, detailed design, testing and refinement, production ramp up, you require prototypes. These are the stars. And you can see here, there are 3 stars emphasizing testing and refinement is very important. Why is that? Because I can say, if you have a idea, I can improve on it. And if I have an idea, you can improve on it. There is no, that is the beauty of the human mind. It can also add and synthesize and bring out something new. So if that is the case, supposing your design fails in the marketplace, who benefits? It is the competitor. The competitor will improve upon it. So it is better to fail in your own idea kitchen, your own idea foundry, or in your own R&D. So world over, what people do, they keep on testing and refining their ideas, and if they think some stage it is done, they keep it as version 1, and the R&D people keep on working on it, so they get version 2, version 3, version 4. Of course, it is not only India, in all over the world, right, copyright is right to copy. If that is the case, litigation is very expensive and difficult, particularly in India. So instead of going for litigation, people should try to maintain a leadership in their design. So how they do it? You have a version 1, somebody will start copying it. So you can release version 2, version 3, like that. So, and again, this is all done through testing and refinement. And testing and refinement needs a lot of prototype to be developed. And people were suffering here because prototyping is not so easy. It needs a lot of skill. Especially we all know, as industrial designers, product designers, we have been doing a lot of these projects right from the early lives to in IDC, and also in our professions, even today, right? So it needs some kind of a special skill, or you need to have a model maker who is trained, who has got the skill level which can suit your requirements. And so people are finding it difficult, clay modeling, puff, cardboard, or breadboard for electronics, or just putting everything together like a toying with the idea. And this was impeding the time to market. And thanks to advent of computing, we have today a lot of softwares that can help us, simulate things, be it for testing or for animation to check the factory layout, for example, or kinematics. One can do, but you can do entire thing, entire product you can do like this. You can even turn it around in a 2D space, giving it an illusion of 3D here. But nobody will fund it. You can show it's working all fine on my computer. You can fund. Nobody will fund it because they want to see something working, which can have a feel of touch and feel, and then only they'll get convinced. Those things we used to do with cut section, montage, and those things, but today nobody will accept that. The model is very important. So again, so this remained, and at this point of time, people started looking at this particular aspect, how to make prototype faster, quicker, you know, and digitization of manufacturing was also happening very rapidly. The computer technology, which helped us to create all these virtual objects, what we saw, somebody was looking at it, called Chuck Hull and Dr. Kodama and various others. They were looking at it, how we can make a prototype quickly. And so a new term was born. It was called as rapid prototype. And rapid prototype is a word given by Dr. Kodama actually. It stayed almost for till 2000, 2005. The technology was called as rapid prototyping only. No other name. And so you can see the world in the third industrial revolution, the 1, 2, 3, the third industrial revolution, we have this 3D printing was born in the year 1986. So in 93 it was invented. It took 3 years to get the patent. So Charles Hull, Chuck Hull, we call him, and he's still there as a CTO, emeritus CTO of 3D Systems. And he invented the first 3D printing technology called stereolithography, or photopolymerization. And now we are actually at the cusp of fourth industrial revolution. We call Industry 4.0, where a lot of things are going to come, further disrupt the world and the world of manufacturing itself. So we all know the conventional subtractive manufacturing is very wasteful because it generates a lot of chips you cannot eat. It requires a lot of energy, so wasteful. And so a new way of making things was born, and this new way of making is directly create a part from the CAD. There is no in between, no intermediary. Those days when people used to have a tutu meme, because you have a blueprint, it goes to shop floor, somebody does. Now it is not there at all. It's all gone, right? Because of the computing power and the capability of this 3D printing. And so it is a regime where we are able to translate art to part directly, without any kind of intermediaries. Though there are, as we go down, we'll see. So we are talking about a technology we can call it as art to part, or CAD to part, where you can get faithful reproduction of your virtual entity into a physical object which you can hold in hand and explore. In fact, this has helped a lot of new developments in product design and quicker explorations. So, and cost of prototyping itself has come down largely. So if you look at the transformation here, the idea to sketch is then converted to virtual model, then it is sliced using a software, and this is the sliced thing is put back, in a sequence in order to get the object back. So it is, in a simple way, we can say 3D printer is a robot which will kind of convert your virtual object into a physical entity. You can also do all these transformations. In fact, many times we think 3D printing is just one word, but it is not one actually. Many people say 3D printing, okay, I've seen it uses fiber or filament. Some people say, no, I've seen some place it uses liquid. So some people say, no, I have seen another place they use powder. They're all right, because you have various technologies today. They all do the same thing, but they're called differently. And collectively, the whole group of technologies are called as 3D printing. So you can have SLA, SLS, FDM, LOM, binder jetting, material jetting. There is one more called DED, and it goes on. And in fact, ASME had to intervene and say, don't call it by 30 different names, but let us have 7. So they clustered it. And so 3D printing by definition is a 3D printing refers to a set of technologies, not one. which help to fabricate 3D objects layer upon layer from digital input data. When I say digital input data, the input could be from a 3D model, a medical image data, or if you scan an object and you can take the point cloud data from there, again you recreate the model. That's how we get the model, a virtual model. And you can see how the traditional process and additional additive manufacturing will compare. I'll come back to why I'm having problem with additive manufacturing term later on. You can see energy requirement also is much less. It generates less scrap because it is additive. And if you very closely look at the part, there could be some problems, but I'm just representatively showing it. And these are the pioneers. We talked about them. And this is the first technology, the first part made, and the humble mission which was done a long time ago, looking like that. But today it's all. So today, modern mission look like this. So let us see a kind of animation wherein you can see the laser comes from the top. The virtual object is sliced, and every time a 2D image is done and it is scanned, and that becomes polymerized. So monomer becomes a polymer with the impingement of high energy laser, you know, and that's how the liquid becomes a crystalline solid, and that process continues. And after the part is made, it is ejected out. And you can see how the part is getting ejected out here. And next technology is powder bed fusion or selective laser sintering. So in this also there is an animation. Maybe I'll go to the next animation. The powder is spread evenly and the laser comes and so instead of liquid, here we use powder. And you can see how the powder particles get bound to each other. This laser is a CO2 laser. It has got a Gaussian distribution of energy. That means it not only binds the two particles in the same level, but also it penetrates inside and stitches it to the layer below. And that's how the part is made. And you can see here, this is how the machine looks like. You can see a phantom writing something concentric circles on the left hand side. That is actually CO2 laser. When it is sintered, you can see it becomes a sheet of nylon. It's a nylon powder. And the process goes on and on. You get a concentric cylinders. And you can see this is called cake. When cake is ejected out, and you are going to extricate these objects, they are like archaeological, excavations. You have to take out the pieces by blowing away the extra nylon powder so that wherever the sintering has happened, the powder are bound, and they make a solid. And because of which, I can make chains, I can make objects that are linked together, without any difficulty. So I can actually have, assembled a part. Because powder, after all, if I make a small clearance, I can blow it away and still get them, I keep saying one thing. In CAD, there is no gravity. So in CAD, you can keep something floating. After you fire it to 3D printing, they get assembled. So only after you take it out of this cake, the part will fall down because of gravity, and you have a link, which is going to form. And of course, you have material extrusion, fused deposition modeling, what we call. And this technology is wonderful, and in fact, it became an open source technology because of the patent expiry. And also there was a project called RipRap. We'll see that. This is make about printing something. And then you have sheet metal lamination is another wonderful technology where laminates one over the other are placed and the laser comes and cuts. This was a technology which kind of they became bankrupt. They could not sell enough, and this technology probably failed. Then there is one more technology came, M-Core, which used the same analogous technology with paper. Even they are not doing well. And of course, Oak Ridge National Laboratories in USA, they are using the same technology with sheet metal. They are still working on it, and a lot of wonderful stuff they're building. And this is yet another technology called binder jetting, where you have an adhesive which falls on a powder, and the adhesive kind of consumes all this, becomes a hard mass. So if you can have a print head which can stencil a particular shape, the powder which goes on the top absorbs it and becomes a sheet. And this is repeated over and over again. And because it is a gypsum powder or rock powder or something like that, it forms like a sheet on which a color printer can actually come and print. A normal print head, like HP, Canon, and all. So you are able to apply color at that particular level, and you get these colorful models. What you see there, and you can see a demo of this, wherein they are trying to build a whole home is built, and when it starts, it looks like a normal house plan, and you are completing the build, then vacuum all the powder out, and you can see because it is bound by adhesive, it is not very strong. You cannot stand high temperatures. So there is no industrial application of this, and so it's not very popular. This is a Israeli technology called metal jetting, polyjet or multijet, what we call. What you see here, floating manifold, what you see here, like it is in zero gravity. It has got a half-white manifold. It has got a O-ring which is very very soft. It has got an actuator below, which is hard inside, soft outside. So the whole thing is printed together. How is it? Here they have a tank A and B. They mix at various proportions, at various voxel level. What is a voxel? Voxel is a 3D pixel. 3D pixel is called as voxel, and you are able to deposit that. So you can build something from transparent to opaque, or hard to soft, or a combination of all this. So this is called as a digital material, wherein they can play around with the property at the voxel level. Voxel is a very small cuboid unit one can consider. And you can see here, it is like paste. When a paste is applied, what is the consistency? Soon the paste gets hardened because of the exposure to laser. And here again, this is a photosensitive material. So it gets hardened, rock hardened, with, you can see a green color. That is a UV light. And of course, people are also doing a lot of metal nowadays. And metal means, metal actually 3D printing goes back to more than 100 years, they say. Why? Because they're able to use a welding torch and deposit beads of metal. And they've actually demonstrated technologies to show it can make vessels or vase and things like that. That is in 1925, 19 in the early 1900 also. People have shown. So people say sometimes metal additive is actually 100 years, more than 100 years old. Well, this technology had to mature itself, and now we have a lot of such things entering the market, and they're still very expensive. We'll come to that when we take up question and answers. And you can see here how the melt pool, the metal, the powder, much like the nylon, they also get fused. But here actually melting happens, and ultimately the material, the whole thing is like a foundry. It's a mini foundry. You can see how a powder bed is getting sintered. This is a powder bed. And metal being very fine powder, it can melt easily at a much lower temperature than your. So they are able to take it to the melting level in a very small area with lasers or plasma, or it can be done with wire and plasma also. So a lot of technologies are coming nowadays, and this is yet another technology wherein a wire enters in the middle. It could be then they're going to have a drop of metal falling. It's called drop on demand. This will transform uh, the industrial world to adapt 3D printing, especially in metal, because every CNC can be converted into a metal enabled mission in a short time with a small console. And also one can do hybrid manufacturing, that is after having done the deposition they can also mission it in the same setup. So such things are also coming. So these are some of the metal printers what you can see. They come in all shapes and sizes. And of course this is a KUKA robot. People have been using robots to deposit things. And many times people uh, tell me that these are not they cannot be called as 3D printers. By definition they are 3D printers because it doesn't matter what will deposit. In fact they can print all around. After depositing in one place they can go all around and they can do. And particularly wherever you have high demand like food printing and all, such robots will do a good job. So if we look at this is called as a 3D doodler. So it works on the principle of FDM, filament deposition modeling. But many times when I ask people, is it a 3D printer? So people will say, the students will say, yes, this is a 3D printer, it's a FDM. But actually, it looks like that, but it is not a 3D printer. Because by definition, the input has to come from a digital data, not from your head. And here the skill of the person who uses like a glue gun or a mehendi, it is more dependent on that. Let us see how it works. You can see. In fact, people have done the same thing with metal and with very low melting point metal like indium and all. They've tried and they were successful actually. They were able to print metal also like this. Lead also can be printed, but lead is of course not good. So people are trying to use other metals. Uh, Probably I'm not able to show today. A lot of such contents are there. And you can see they are able to do even on a different plane. So these are the capabilities what robots can offer. In fact, robots can uh, transform the whole 3D printing market because they have many functions to do. So I foresee that robots would soon replace the so-called boxed 3D printers. So in the world, there are many things are additive, but they are not 3D printing. For example, you have natural wood. Wood is additively made by nature. Pearl you take. Pearl is a deposition of calcium, salts and all, layer upon layer. It is again additively made. And human beings born in 9 months, again it is additively manufactured, multi-jet, because you have a bionic camera like eyes and you have a CPU, you have whatnot, a pump and a stone like bones and soft tissue and skin which is able to sense so many things. It's full of sensors, skin is full of sensors. So that means, nature, nothing to beat nature. But I'm going to show you something man-made actually. This additive, but not 3D printed. और बूंदी को लगा के, with sugar syrup, you are able to bind them together, bundi ko. Then you are going to make a ball out of it, spear, and so it becomes a sweet. And of course, this is also another wonderful example. The beauty of this slide is, in additive manufacturing, in a sandwich you put tomato, it becomes a tomato sandwich. You put chutney, it becomes a chutney sandwich. You put cheese, it becomes a cheese sandwich. So very clearly, if I can play around with a layer, I can bring in many things. So that is the beauty. In additive manufacturing or 3D printing, we can play around with that layer, and I can, that is something which is missing in conventional manufacturing. And so I was talking about Dr. Adrian, who started working on this printer prints itself concept, parent and child. And in fact, people started, writing such cartoons. Today, in a way, it has become true. And today, um, such open source have brought in a lot of things which are analogous to FDM, and they come in all shapes and sizes, and capability wise also. And today, this additive manufacturing or 3D printing is making deep inroads into jewelry, medical, FMCG packaging, lifestyle, architecture, aerospace, automotive, electrical, electronics, white goods, plastics, and the list goes on. It is only limited by imagination. And you can see these are the objects which are unimaginable, and unthinkable, unmadeable, unproducible, or all that, all kinds of fun. But it is today possible. And how they were made? They were made by a complex mathematical formulas. You start, substituting n is equal to 1, n is equal to 2, n is equal to 3. And so it will transform on the screen. And when you see a very interesting object, you freeze it, export it, and then you can print it. And it can be only done by this technology, 3D printing. Because it is going to give you a really great dexterity in terms of making any complex thing. It doesn't demand anything additional expense or facilities or setups, for example, which is very much required. So if I want to turn something round, I need a lathe, or I can also do it on a milling machine. But if I want to do a square, I have to mill it at 90 degrees. If I want to do a hexagon, I have to index it. All those things are not required. So in conventional manufacturing, you need so many setups. You need jigs and fixtures. Here, nothing is required. That is the beauty of it. And in fact, the whole world is adopting 3D printing for for these reasons. What you see, 6 of them. One is part consolidation. That means you have 20, 30, 40 pieces, which makes one subsystem. You can probably combine all of them. It's called part consolidation. Okay, and one can do on-demand jigs and fixtures very easily. In a matter of few minutes to hours, we can make it. And need for lightweighting is very high in airborne systems, like aerospace, rocketry. You require a payload has to be optimized there, so dead weight is not acceptable. So material with high strength to weight ratio are selected, and you're able to create the voids so that you make it lightweight. And this is not possible to produce by conventional CNC or die casting or by injection molding. So the only way you can produce is by additive manufacturing. And complexity, Indian jewelry is most complex that way. So complexity is something you can handle very easily. And world is looking at one-off pieces many times. And especially with the population full of millennials, the Gen I, Gen X people, they want to celebrate their lives, and they want to enjoy something new and unique. They want to design themselves. So such people, such demand is coming, and that can also that is also addressed by additive manufacturing in a nice way. So need for one part is addressed by additive manufacturing. Need for customization, it could be my own spectacle lens, which is unique to my power. And likewise, there are a lot of things, especially in medical, surgical enablement, making prostheses or orthotics or any such device. You need to make it specific to a patient or a person. So that becomes really difficult in a line setup, a production line kind of manufacturing setup. So it needs extreme agility. And that extreme agility is offered by 3D printing. And so people have tried to print big, and people have also tried to print small. This is about the capability. And people, in fact, make big things not because they have a big printer and they can have a small printer. Using that, they can digitally cut the model and then print the small pieces. They can be put together with a lot of nice glue. We have a lot of specialized glues which will not break at all, and so you can put the whole thing together. You can create a memo that you see in the background from the printer, which is so small, which is in the foreground. So the whole industrial shop floor will look like this: no oil, no noise, no humming. Most of them, they run on batteries, and it's clean. Air is full. There is no need to. And also they operate in 20 degrees and things like that. So it's a very comfortable shop floor. And in fact, when we speak of 3D printing, there is no economy of scale. That means if I make 100 or I make 1,000, the prices will not so much fall. No economy of scale. Conventionally, if you make 1,000,000, the landed cost of the part will become very, very less. That is the beauty of the mass customization or mass manufacturing. But today, we hear more and more of mass customization. And it is a misnomer. Mass customization has a real value add, and it is available at a mass price. That means it is low cost. At the same time, it is customizable. That's called mass customization. Anyway, today we'll not go in deep into this. That is a big world by itself. And complexity, when it comes to conventional manufacturing, complexity will add to cost. Whereas in 3D printing, no matter what you are going to do, a cylinder or a very complex ganesha, the complexity wise, machine doesn't discriminate. And you can see where exactly 3D printing today can be used. Whenever you have complexity and very low volume, 3D printing is best. Even today, when you need large numbers, then you need to go for all those design for manufacturing, design for assembly, design for that, design for this. But 3D printing, when we say it gives you extreme design freedom, cannot do a high volume even today. But somewhere we are going near that in a very, very slow way. That's why it is not a revolution. People are not adopted to 3D printing like smartphone, for example. In last 5 years, smartphone people have really, never thought that they will be using every one of them, right? With all the color display, and we had the luxury of the gyros and so many things. But today, 3D printing is 35 years old. Next big thing people say even today, but this is there for 35 years. So it's a revolutionary technology, but it is showing the evolutionary growth, right? And so we can see the growth. What started in '86, which was capable of only making prototype, mock-up model, dumb model, it became more accurate, so you could do the design validation. And then today, we are somewhere close to making end user part. So why I say somewhere equal, somewhere near, because there are still real world needs real hard material. Uh, in the use context, you require a lot of high temperature, high toughness material, and so many materials which are not possible by additive manufacturing, largely because of the R&D also. Material R&D for additive was, it started much later because people were still toying whether it works or not. But today, I think there's a good roadmap, and a lot of companies are funding material research, and that is the way it goes. Hardware may get saturated, but the material development side, the software development side will really take this, make this technology kind of child's play. That is the beauty of technology. And the future of 3D printing is moving beyond prototyping to end user part. And of course, material, there are a lot of materials, polymers, metals, and others is a big one. It can be even medicine, it can be glass, it can be diamond, it can be anything there, gold. And the material input will be various forms, liquid, sheets, filaments, or powder. And you can see still today, metal additive is a very, very small part. Photopolymers are there, and thermoplastics is also there. Slowly, metal, see, only with the metal growth, you can actually see industrialized 3D printing and transforming the world, But 3D printing has its own sweet spot, which others cannot really compete with. That's where it adds value. And so technologies are becoming faster and faster. What used to be 11 and a half hours, it has become 6.5 minutes, apple to apple comparison, okay, across the technologies. And this is not, this is quite an old slide, but it is still, every day it is improving, And these are some of the technologies we have at Imaginarium. And you can see, if you see the technology, all, whole lot of them, you have small, big, and you also have bioprinting. Bioprinting has been a great interest in all the universities now, including IIT Bombay, IISc, IIT Hyderabad, world over, for example. People are trying to do biofabrication, organ printing, organ fabrication, so many things. People want to print food, meat getting printed, and things like that. And we'll come to that. And in fact, prototypes for which it was born, the whole technology, 3D printing or rapid prototyping was born. Even today, 70% of 3D printing is used for prototyping and development. Maybe of this, there could be 50% of for production, 50% for research also. Product development and for research also. What I'm trying to say is this virtue or this capability, what this technology has, is still being used today. So scale models people are trying to do. People are also doing full scale models. So this we did it for Vasirani, Chunky Vasirani, and this is India's first electric hypercar. So many parts are all 3D printed. They are putting together all this. This is a dummy model. It is not a real running car. It went to UK and came back for a show, and it is somewhere in Andheri West. It is now being developed. They are developing the interior now, and also they are looking for funding. And so a whole lot of stuff can be made by 3D printing. In the early days, all this FMCG packaging things, automotive things, mirror optics, they're all being done to simulate. I remember in Auto Expo, many of these things are all made by additive manufacturing. They look they look like real, and some of them, the work they like real with all the capability, but they are 3D printed. In fact, in metal, the greatest advantage of metal is very expensive, but one can derive maximum benefit in heat exchangers, where the surface, um, it's the surface property, exchange of heat and mass flow, and so many times people use additive manufacturing for that. That's the best actually what you can think of. And in fact, jewelry hitherto was considered to be a piece of gold. Now it is no more. One can actually freak out with designs, have anything, and get it printed, enjoy. It need not be gold always. And so it is actually defining a new aesthetics. So Titan, in the early days, they wanted this to be done for a fashion show, and they wanted a flexible material. Those days, the flexibility was not there. So we made a master and we had a silicon mold and injected a flexible material, elastomer, to make this. So there's a lot of jewelry, but we made it. So you can see the new aesthetics taking advantage of what can be made. So people have been toying with this and it adds value. So the lightweighting, besides aerospace, automotive components, in jewelry also, people like this Voronoi diagrams or network or such structures, on the surface. So it retains the shape, at the same time it reduces. People want to show more gold, but they don't want to pay for it because it's very expensive. So people love this kind of. It can also make it breathable, breathing. It doesn't trouble. You can see here some of these. So people have been trying to do many things. Customized phone cases and all. People have tried. Somebody thought it is going to be a big business, but I mean, after soon people, it's like a child toying with something, and after that it'll break the toy and start making new things out of the broken toy. Same thing happens with all of us. So people had fancy for all this, but one can want to do on demand such things, and you can see these are some of the capabilities what we have, uh, and really creating a sense is making these parts which will really bring in evaluation of ergonomics, aesthetics, finish, all that quickly when you are doing your product development. So it will, at a fraction of cost, you're able to do, you can cut down on time and get all these things done. And many times clients will approve of this more readily because they're able to see it. So there is a quick buy-in from the client or your design department or marketing department or whatever, whoever is the funding authority for VCs, for example, for the startups. So these are some of the use cases I want to show quickly. This IoT device and this yet another. You can see they come in all kinds of shape. They always not complicated. Here you can see some display here. These are all for the IoT. This is made for Blue Star. And in medical, typically there are 6 levels. The first level is of devices. Second level is of making models, big or small or 1:1. A third level is making jigs and fixtures for surgery, stunts, dentistry, all that. And that fourth level, making an implant which is going to be inside your body till your entire life and beyond. Then you have drugs. For children, they want to consume a pill, a medicine like a jujubes or flower or smiley, those things. And people who use multiple drugs, they can probably put all of them together and make one pill instead of taking 10, 15 pills. So that is also being looked at, if we can do it. So still there are a lot of challenges here. The last one is the tissue and organs. We are at 4 levels. Fifth level, it's an experiment. Sixth level, of course, we are also watching it. There is nothing ready because vascularization of cell is a long way. You know. So the God is playing hide and seek. And people, of course, they are trying to do. They can grow a cell on a petri dish. They can deposit on a scaffold, and but it will not work like an organ. A long way to go because every cell has to get its conductive tissue, blood vessels, capillaries, which have to take the food and take back the excretions of the cell, and individually they're all living cells. And so today this is called a vascularization. That is a big challenge. So that's why people have problem here. And of course, we have also done many medical projects, devices. Like this one is a braille trainer, Annie. It got funded from British government, in fact, the Crown. And this is yet another product called hypothermia monitoring device for Bempu. Bempu is a company in Bangalore. And this is a breast scanner, eye breast. And this is also made at Imaginarium. This is a health band. So this startup, they wanted just 6 of them working. So we made just 6 of them working. And of course, sometimes we also get requests from the pet shop. So we designed broken beak was restored for this parrot. And so it's fun, sometimes working with them. We don't charge anything for them. And in Industry 4.0, whole world is looking at, I think 3D printing forms a very important aspect. Together with CNC and robotics, they form a holy trinity, and they bring the physical side of cyber physical system. So I have been telling design will lead consumption management will be taken for granted. So this is going to happen. And you can see here, I think some of the slides are repeating. I'm sorry about it because I could not edit all of them. So you can see here, this is a AI-powered finger ring. And this was made at Imaginarium. You can see a small display on the right-hand side. So one can take the phone calls, one can read the messages, one can make payment using this, authorize a payment using the trade. And so a lot of other things this can have. And so we have been empowering such startups to, in fact, they have now changed the name of this company because it's fast changing. And you may wonder, what is this? It looks very funny. In fact, you can see on the left-hand side, there is a spiral there. And the spiral, if we have the compressed air coming in the center, these two will become bigger. And the center part is like a tongue. They come closer. So let us see an animation. You can see here how this tongue is working. This is called as a compliant mechanism. The compliant mechanisms are mechanisms which have no moving parts, though they move and actuate. Bill of material will be just one, no springs, no joints, and that's the beauty of the compliant mechanism. And they have a very long life because of no wearing material. You can see the customization is going to reach the end user. So much so that a common product like a razor, is being tried out with such offer where the end user can play with it. They can order anything which is, whenever they order like this, they're ready to pay more. They're also ready to wait for some time because it is customized. So with this, 3D printing only can answer such agility. When we look at the line system, it is made for a particular assembly line, it becomes very difficult. So the promise of just in time, what the Japanese promised, is probably happening now because of 3D printing. So the future is all about building world smartly through uh, reliable technology, acceptable quality, uh, with a lot of material research we need for the real world. And all these things can be controlled from a distance. And they are going to uh, provide support and service in the product life cycle. When we talk of product life cycle itself, it is coming down now because when we talked of the early cars, uh, they were there for lifetime. You know, some of them maybe 30, 40 years. You know, today it's all coming down. You know, even the development time is coming down. Life cycle is also coming down. You know, and so for a smartphone, the life cycle is for me it is 3 years, and for youngsters it could be even less, 6 months. You know, they want to change the phones. So when you say predictable results, it is in that life cycle. You know, you make it work and its useful life and retirement. That is predictable uh, life wherein it should perform. You know, so people are able to actually see. You know, and in fact, people are going to heavily depend on the cloud in future. So we built a cloud factory. You know, luckily for us, we started research in 2016. By 18, we had a cloud factory platform ready, and so today only a very large OEM and all they will go for all these printers. Rest will adopt to cloud factory. No matter where it is made, who is going to make, whether it's 3D printed or not, who cares? They want the product to be delivered. That's what happens. And you can see 3D printing, you know, is going to soon go out of the boxes. In fact, they move and they are going to be in a room like what we all live in, you know, without the need for a special atmosphere or uh, you know, special environment and all that. And these robots can transform, build all such big things. This is from Relativity, a competitor to SpaceX, and they are building a lot of rocket fuel tanks and all that by this metal wire based uh, welding type of 3D printer. So it's a wire based one, so it's much cheaper compared to the powder based metal 3D printing. And I think with this, we come to the end of almost end of presentation. So when we talk of this 3D printing, we sometimes forget a lot of other stuff which are important even before we reach to 3D printing. They are idea or design. Uh, what is the need you want to address? Then, of course, that is a design part. Then you do the CAD embodiment design. You know, then of course reverse engineering can be used, AM can be used. Then you always require a pre-processing of files before it can go to 3D printer. 3D printer itself need material on one side. It also requires a lot of machine care. And that is also very specialized for these. And this doesn't end. You need to have a post-processing. Almost everything which is 3D printed has to be processed in order to use in this world. Then, of course, it opens up a world of opportunity, which we have seen now. And so, in some sense, we started with a sensation, fashion show and all, and we saw a lot of use cases where industry is using in making products, in making devices, in making even medical devices, which are very useful. And in fact, Imaginarium has at various levels. You know, we have different verticals. The one which is having this care-like thing is rapid. The left hand side you have, if I'm going anti-clockwise, I have a ring that is precious, then you have life, then you have solutions, and you have academy, and you have a venture fund. So these are the various verticals we have at Imaginarium, and we have been spurring the industrial growth through our enterprise 3D printing. We have about 25 production 3D printers, and we have CNC, we have tooling, tool making capability, we have plating capability, all in one integrated setup at Andheri. And you are most welcome to visit us. At this point of time, I'll stop. I have taken actually more time, and I wanted to keep it short, but I think it's important to take you through all this. I stop here. I would like to take your questions now.
So maybe let me just ask the first question while we are waiting for
Yes.
others to, warm up to questions. So, what's the size of the 3D printing market in India, and how has it been growing?
Well, market is very huge actually, because market is, in a sense, the opportunities are very high. Many people have not even fathomed where it can be used.
No, so my question is not more like the opportunity, but what is the current, maybe the revenue?
Okay. Revenue wise, I think it is about 3,000 crores. 3,000 crores,
Okay.
largely hidden in aerospace, medical, automotive.
Hmm.
And whole of jewelry, which is our flagship in terms of this thing, is also enabled by heavily enabled by 3D printing. Because in 3D printing we go to the near nut shape. You take a product, it's like a nut shape. We say net means net gross weight. We say no. So it is not net in the sense of a fishing net. It is the net is gross. Okay.
Sure.
When we say net shape, you are able to go to the net shape very easily. For example, if you want to make a Ganesha, you start with some primitives and go to the Ganesha, either adding or removing. In 3D printing, you go to the nearest to the final part, net shape, very close. That's where we tend to benefit. And so people are looking at it, and especially in jewelry, where the gold loss is very high. You touch gold, you lose the gold. It is becoming very, very important for them. And in medical also, the fit and finish, and biocompatibility, bioimplantability, bioabsorbability, all these are very important. So that is also driving, kind of uh, adoption very easily. And but we are having, industry is having a 100 years or 200 years of thinking inertia. They only know the old ways of doing things. That means I should not look at 3D printing a washer. I should not look at 3D printing a lamp post. I cannot 3D print a rail for a railroad. These are all stupid applications. But people who don't know, they may only think like that. So in fact, we have to unlearn the old ways, learn a new way by which you are able to bring in the beauty, the real worth of 3D printing, which is complexity, which is agility, which is bringing something which never existed before. Optimization to its maximum. Many times people don't look at these, because they are not aware of it. Yeah. Thank you, Umesh.
Thanks, Guru. Well presented.
Thank you.
Connect again.
Sure. Thank you. Any questions?
So how is your even
If
your
somebody,
yeah, sorry,
if somebody wants
Gunanidhi, go ahead.
to get into 3D printing as a more like a hobby, what's
Yeah.
the best way to start?
Well, I think you can make your own printer. We'll help you make your own printer. That will be a lot of fun. You know, I can teach you how to make a printer.
Yeah, that will be nice. I will connect with you.
Yeah. In fact, whole internet, there are a lot of open source things available, and today there are a lot of shops also available. And of course, whatever you assemble, in the first go, it doesn't work at all. I say I'm radio operator. I know any circuit I try to rig up and join them, they never work. You know, then goes the learning why it did not work and how to make it work. You know, but if you don't want to have these headache, Gunanidhi headache, you can always buy a small one. That is assembled kit. Also, you can buy. You know, so wherein you can start exploring, but once you get some kind of proficiency, then you can think of making one. But I think making is very easy, and it is really adventurous. You can do it easily. We'll give you helping hand.
Tanish, tell mom not to call
Thank
me.
you.
वो मेरे यहाँ पे आ रहा है.
Welcome. Anybody? In fact, I took a module to NID MDes students on mass customization, and that was for 15 days. It went on, and where we actually went deep into the CAD and how to make it customized, how to make it, how to make the interfaces where people can. It is like mass, not mass customization modules are quite interesting actually. Probably I can present some other day.
Yeah, so one question I was asking is, what is the growth that you have seen over the years? I mean, your
Okay.
company itself,
Okay,
how much has it
so
grown?
cumulative growth year on year is varying from, it used to be 15%, it
Hmm.
increased to 20%.
Mhm.
Currently it is 24%. Okay, and so definitely it is growing, but it is not growing faster as we expected. You know, always like Moore's law, it has exceeded more. You know, beyond that, uh, there are big. This is because of a lot of problems this technology has. When we say it is great and all, it is still expensive, and the material cost is still. When it comes to metal, it is very costly because people, when they want to optimize the powder to put them together, the automation of metal is very expensive. You know? And so the feedstock raw material, what you call, is very costly to start with. And so I cannot or I cannot do a lot of things, trial and error in metal because of its expense. And for me, the growth is in metal, not in plastics. Plastics, yes, it is there, but real world needs metal. You know, a lot of industrialization needs metal, not only just steel, but every kind. So you have more etching steel, you have titanium, you have. The beauty is, additive manufacturing has made the man's desire to go beyond, a solar system, probably coming to come true because we are increasingly able to uh, play with metal, which were exotic metal, which were unable to cut. The alloys of molybdenum, vanadium, tantalum, and things like that, apart from titanium, these are highly refractory metal, right? And so additive manufacturing is taming those, because we are playing not with the bulk of metal but with powder. And that way, in aerospace, additive manufacturing is going to play a great role. Not only that, for example, the space structures, people want to build some structures on Moon or on Mars, is perfectly doable. It is not a science fiction anymore, because people are simulating here on Earth using those type of. Coming to one more thing, India Inc. Is looking at ROI many times. They're not looking at the disruptive nature of the technology. It can give you 10x or 50x or 100x kind of value add, which people are not looking at. So it is very important that we look at that instead of saying, comparing it with making a washer by press tool, blanking and piercing to 3D printing. This is a wrong way to assess its value. So people have to unlearn the old ways and learn the new ways. And with artificial intelligence, simulations, generative design, algorithms, people are able to mimic nature more readily than before. Nature is full of complex structures, organic structures, which were hitherto not possible to make. You can imagine them, but you cannot. You can see them under microscope, but you could not imitate them. Thankfully, today it's possible, thanks to the technology, 3D printing. We are able to do such organic structures, be it a lattice, be it a generative design, or topology optimization, what people call, all very close to nature. So I see that structures tomorrow may look more like a spider. A JCB may look like a spider than what you see today. Massive, because it's highly optimized to the task. And it's so organic that no other technology but 3D printing can print it. That's the only way. And the buildings are also, people are trying out. These are all concept proving today. But as the technology and other things, raw material cost come down, the adoption will zoom. Right now, I put a global 3D print, conventional to 3D print is 3D print is less than 1%.
That's also quite high. I mean, 1% is quite high.
No, 1% is also not. I'm not saying it's less than 1%.
Less than okay.
Many others also join that
Sure.
1%. Yeah, unconventional things. Yeah.
Achitaji, I think you had a question.
Hi, Gokul.
Yeah, Gokul, go ahead. Gokul, we can't hear
Hi.
you.
Now, Gokul is an expert in 3D printing.
Gokul, sorry, we can't hear you.
Okay. Hi. Very specific to metal 3D printing.
Yeah.
And to the field of injection molding tooling.
Yeah.
Where do you see it stand in terms of being cost effective?
Well, I think conformal cooling channels, though, very wonderful, very expensive. Okay. And so people are not finding it very good, when it comes to cost wise.
Okay.
Having conformal cooling is also conformal cooling, very complex coiling what you have. Finishing them inside is quite tedious.
Okay. What about only, let's not look at only the conformal cooling capability, which is a 3D map of the actual product's geometry. which no other technology can give, but 3D printing can give. Looking at basically what you call core and cavity making for complicated small parts. Let's say you make an electronic connector or
I
things like
think
that.
I see a lot of opportunity for small parts. Okay. And if you can adopt a insert kind of approach,
Okay.
we should not waste in bulk material cutting.
Agree. Understood.
You have a shell, for example.
Right.
If the shell can be made with a very hard high carbon steel like Moore-etching steel, tool steel, I think it is good. It can be done.
Okay.
It gives you superior tool life, superior finish, and better cooling. You know those things. But at the end, if the OEM is squeezing you to make a part at 1 paisa, 2 paisa, you have to do somehow. Then sometimes it may, unless these processes inherently come equivalent to conventional, they don't see adoption.
I'm just wondering whether if it's a small part needing, let's say, a lot of very fine ball cutter machining and a lot of fine EDM to be done, in comparison, maybe getting a metal 3D printed core would make sense and be more viable. Would that make sense?
Well, I will, as a practitioner, I can say that very fine something, what you have, would also require a very fine layer thickness.
Right.
Because resolution is something, is a problem with 3D printing right now.
Okay.
And when you machine and you harden and you have a work hardening there, work hardened metal are much better in finish than 3D printed, which is layer by layer. So for that, if I can go for micro stereolithography, for example,
right,
it may give you, because people are actually trying to print what is that called, dermal patches, microdermal patches, which are like injections, which are very small, pricks like, so you put it on the thing, skin, it acts like a kind of a plaster, but it delivers the drug. So people are trying, but if you see that, again it needs a very fine layer thickness. Otherwise, it has got staircase effect, for example, which will be a problem. But what I have seen is, we work with the 16 micron, 10 microns, 25 microns. They are much better than 100 microns, And FDM, which is at still 179 or 178 micron, is quite coarse, But coarseness is okay for a large part. But when you are looking at a small insert, when you said there are fine features, I don't think it is possible. There, if at all you go for, you may go for a secondary process, in order to further finish it. Or forfeit.
So just to get a feel of it, if I were to make a punch for a Bisleri bottle cap, which has an internal threading, so rather than do it the conventional way, if I were to use metal 3D printing, would something like that be a ready-to-use kind of an insert, or that will also need some kind of a conventional diamond paste polishing and those rest of the thing?
Well, I think every tool, whatever you make by conventional or otherwise, needs to be touched. And as I said, additive manufacturing is always, it needs post-processing. And when you have a burr or a pip, you need to definitely get a better RA value for ejection purpose. Otherwise, they won't get ejected properly. There can be local burning also, charring also of the plastic, all those things. Yeah.
Got it.
Thank you.
Thanks. And congratulations. I'll take this opportunity to kind of admire the journey of yours and the mastering of this entire ever-changing domain.
No, daily we are learning, because technological obsolescence also very high. So it keeps us on our toes. Yeah.
Appreciate.
Thank you. In fact, Gokul knows the A to Z of this technology. He's simply asking me questions. He's an expert himself, you know. You know.
That was a long time.
Yeah.
Gokul, we need a session from you then.
No, I'm not. I'm a user of this technology.
He's a user.
So I get a lot of.
He's an extensive user.
Okay, great.
I'm a daily user of this technology, and
Correct.
once upon a time, I really explored this domain to make it all happen. Then later on, continue to be on the other side as a consumer, rather than the creator of this. Okay.
Right.
So I had to use it day to day. That's what it is. Okay.
Thank you, Gokul. Any other questions?
Is it difficult, or is it very not very common to use the reinforcement in the 3D molds?
Well, 3D mold, normally it is very difficult to use reinforcement, but people have started building houses and all, no? So it is a kind of a macro. When you see, we talked about microstereolithography, which is microscopic, and whatever we saw is a little bigger. We also have people are trying to build on gantry a large, concrete pouring 3D printers, wherein people are also using some kind of reinforcement, like sheets and all, sheet of metal and all that, because it has to be, it comes very slowly. When it is pausing, people keep it on the top of it. So that kind of thing I've seen.
That's more like a manual process, right?
It is a manual process. That's right.
If it's like a product, like a plastic product.
Yeah, a reinforcement. I'll come to that.
Actual strength, right? It requires some kind of a reinforcement.
Exactly. So it is possible. There are two ways of doing it. One with laser power. Varying the laser power, one can have a different structure. The properties, toughness to hardness to transparency to opacity, one can play, number one. Number two, I told about two different tanks of two different material, the hard to soft and transparent to opaque. So this is called as polyjet. Okay, polyjet means it has got a number of nozzles through which material of different properties, they come and mix, and they mix at a voxel level. Voxel is a very small 3D pixel. So you're able to make functionally graded material. That means you're able to, so if that is the case, you can actually make it like a reinforcement. For example, we have built a human hand with hatti inside, which is very hard, and outside very soft exoskeleton kind of thing. Soft material, not exoskeleton, I mean the soft tissue. So then for a Jaipur foot, for example, which is a composite, we can print it as one. So the though it is going to be very expensive, if we can combat that technology and patent because of material and all, it is very costly. But if it is taken care, this will be an efficient product. Much better than what you see, the fabricated one today. So if you come to IDC, Chakku has worked on one project where they did a lot of good work of ore molding them. But same thing can be done by 3D printing in one go. In polyjet it is done. So people have tried to make things with gasketing, which is soft, and outside manifold, which is hard, and the actuators, which are soft to touch and inside hard, things like that. So if we look at it, it is possible to actually have reinforcement inside. So one can play with different metals also. We can play with different material also. We can play with the smart material also. wherein you can these common smart material I can find is the bimetal. Bimetal it behaves because of temperature expansion, one side more, one side less. So it's going to bend and it will actuate a switching or non-switching, or switching off. So that is a smart function. But likewise, for different stimulus, people are able to actually control, holds. So people are able to make mini robots for drug release. Even for space application, they are able to make actuators, which are smart. Depending on whether they are in sun or they are in dark, they are able to do certain things. Or pressure, low pressure, high pressure, or temperature, they can do some things. So these are called smart materials. So having smart material in 3D printing would bring in some things which are hitherto not doable. So reinforcement for buildings, it is done in a indirect way. Supposing you have carbon fiber and all, which are or PEEK, for example, is very strong. If you can dispense it, wherever required, necessary, then it becomes a reinforcement. So if you are addressing at a layer, why not? It can be. Right now, today, people are not finding such examples readily. But I think people are trying with conductive polymers by making PCBs, which are possible to conduct. They are also embedding the conductive polymers, which act like a sensor to make the digital twins possible. That means a gear will have a sensor, and that sensor is not, is embedded inside because it is made that way. So what they do is a conductive polymer track is left. By inductively it will couple to another receiver, and so as and when in the working condition, they are able to monitor the gear, or it could be a rivet, or it could be a beam, like that. So people are embedding a lot of such intelligence into the uh, uh, you know uh, mundane products, where you can actually monitor them, observe them, and you are able to it's all really becoming, if all things are getting tried, they'll become part of RFID, for example. Antennas can be printed by conductive polymer. So you have a polymer, and based on you have a conductive thing, and then you have again an insulator. So the whole thing behaves like an antenna now. So things are possible.
So, Guru Prasad ji, I think this was quite insightful. I think there are a lot of information. For me, all this was quite new because I am from the visual arts background, and that's where I do most of my work. But I think the rest of them would have got some real, some good application that they can start, or maybe start 3D printing at their home. Who knows?
Yeah,
Like
true.
Gunanidhi said.
Yes.
And I think we should definitely.
Very inspirational, actually.
Thank you.
Sure.
I thought maybe I already know about 10% of 3D printing probably, but now I realize that I probably knew only 1%.
No. I will also say the same thing, because more you learn, more you know. A lot to learn, actually, that goes on. And definitely, you're most welcome to visit Imaginarium. Sometimes I give a virtual tour also. Right now, we are making a film for a virtual tour, so that sometime. But when you're in Bombay, you're most welcome, all of you, because we are very close to the airport, T2 terminal. It's only about 10-15 minutes. And we have volunteers who will take you around and show. And Gokul, of course, he has come, I guess, with his son. And Thank you, Purnima.
Okay, and I think maybe we should just continue the discussion on the WhatsApp group, and we can
Yeah, sure.
close the talk
Nice
now.
to see you. Mohan. Mohan, show your face, no? Ravi Krishnan, I have not met you, but nice to meet you. Tanishq, of course. How are you, Tanishq? Muralidhar Reddy, I have met you in IDC event.
Yes, sir. Yes.
We really love your wooden explorations there.
That's
Lot of
our
good
material. Sir. We can't 3D print it.
No, they have tried to 3D print that also because with PLA they mix the sawdust and people are able to make a wood-like material. Very interesting. So we should connect on that.
Yeah, that must be the most challenging because the wood has a grains, right? There is a direction to the grains,
Yeah.
which is what gives that typical.
Yeah, it will not give that. Yeah,
that would be really interesting.
Yeah, but in a way, it should be possible because if we really control the voxel fill, and voxel being very very small, why not? It can be done, but at what cost is the question? Whether it is worth it when you are naturally getting something, synthesizing something, unless it is an organ where you cannot make it, people are ready to pay. Many times people say, water bottle cap, if I can make, it will cost you 500 rupees. Why would you want to pay 500 rupees for that? But if we say the same thing, you 3D print it, it is going to cost you 2 lakhs and it is going to save your life. And so if it can save your life, then it's a different value proposition there. And that's where 3D printing comes into play. But all said and done, a lot of product designers are enabled by because fail early, fail fast is the main advantage of these prototypes. Fail early and fail fast, so that it doesn't. It will control your useless explorations in that field where you can know it's going to fail at the end. So that can be done much faster. So that's why people are using it as a very strategic design enabler, design tool actually. And for even exploration, I remember we had made some concept for IDC Professor Sharma. Mobility, when he was developing some concepts. So actually he could meet the funding agency with that concept, which was made quickly. And so he was able to convince. The same thing happened when Raja sir approached me with the alumni fund and those hands which are there. On the way to library, if any of you have visited IDC, the main library, which is the Institute Library, there is a small octagonal island. There they have put 11 feet tall hands like this, which are made from the steel taken out of the broken the corridors and all buildings. And they wanted us to make matching 3 hands, which are more feminine. They were 3D printed and they were mounted. So it's an installation by the alumni funding, designed by Professor Raja. That execution when we did, it's quite strong. And by the way, I've used reinforcement there, Mr. Hegde, because the parts are so big, we have to use some reinforcement. We have done it. Yeah.
Okay, I think we are well beyond the 1 hour time. So let's close this here.
Thank you.
And we can continue the discussion on WhatsApp.
Sure. Thank you so much.
Okay. Thank you guys. Thanks. Thank you so much.
Thank you. Thank
Bye.
you one and all. Enjoyed meeting you all virtually. Thank you.